Everyone. We're going to start pretty much right on time today, just because we have a lot to cover in the next 2 days. That's all we have left for learning stuff, right? We're going to have our exam next week on Wednesday. On Monday, I've put our potential survey times out. So I know it's a holiday, but no one can really do anything, so I figured we might as well put that time to good use. So I've put some like a doodle poll up, so it'll just give you a couple options of which one you want to sign up for. Presumably there's going to be 4 group interviews with about 4 people each, and they should take between half an hour to 45 minutes. I've also put one for Wednesday next week after the exam. If it turns out we need more time slots, I'll come up with something. So. Okay, so if you wanted to participate in that and you can make one of those time slots, go ahead and go to the Helpful Info Polls channel and take a look at that doodle poll. Alrighty, so last time we talked about chemical reactions, right? We had 4 different types. We had the synthesis reactions, which were just combining 2 things into one thing. Fairly straightforward. We had decomposition, which was the opposite, where we would take something and break it apart. And then we got into more complex ones. We had the replacement reactions. So we remember with single replacement, we're going to have a compound and an element turn into an element and a compound, right? We are going to have something kick out one component of a compound and replace itself there. Let's see, someone gets to get muted. Who's it going to be today? Maybe it's Melissa, we'll see. Or maybe they've muted themselves. Yay, Melissa did. Okay, good. Alrighty, and so we remember that metals will replace metals, and non-metals will replace non-metals. And then we also remember we're not going to mess with polyatomic ions. Okay, so keep those alive. Remember also with these single replacements, we do have charge changes involved. If it's a variable charge, we're going to assume it's +2. Alrighty. Let's see. Okay, then we did some examples. We went into double displacement then, which is where both compounds will switch partners. So you'll have 2 ionic compounds. They're going to just switch partners. So the cation from one will go with the anion from another, and also the other way around. Remember, we're always going to charge balance our compounds properly. And we are not going to change the charges. Okay, so we remember we did a couple of examples here. And then we also saw that there were a couple things that if they were to be produced in a reaction, would be unstable and would break apart. And those would be carbonic acid, sulfurous acid, and ammonium hydroxide. Alrighty, so that was our quick 5-minute cover of last week. Let's continue. So I have here, we're going to do combustion reactions. So these are easy, the easiest one to think what the products are going to be. All right, so combustion is going to be something that's got carbon and hydrogen plus oxygen gas. All right, this part is a combustion reaction. All right, and this will always produce 2 products. And that will be carbon dioxide and water. And while in reality we may get other products like carbon monoxide or other things, we're just going to assume we have perfect combustion in this class. And so for any combustion reaction, all you will get is CO2 and water. It does not matter what your X and Y's are for your hydrocarbon. Whatever those may be, you're going to combine that with oxygen and it's going to make carbon dioxide and water. Nothing else. It'll never change. So if you're ever asked to predict the products of a combustion reaction, it's always carbon dioxide and water. Just so you know, sometimes you might also have oxygen present in your reactants. So, for example, if you were to burn sugar, that would be a combustion reaction. you would have C6H12O6 plus oxygen turns into carbon dioxide and water. Okay, or you could have something like propane. That's, C3H8. I'm not going to make you memorize that, of course. You'll put that with oxygen. And guess what the products are? Please don't get this one wrong. That would just break my heart. Who's got the answer? Alright, Samvel's got it. Let's see. Yay! Though technically you put cobalt, it'll be... Okay, I got you. Yes. No carbon monoxide. Okay. Yes, any combustion reaction, the products will be carbon dioxide and water. Okay, so for right now, remember, we're just kind of looking at what the products are. We don't care about these 3s or 8s or anything right now. Hi, Rob. Okay. Uh-oh, someone's being loud again. Let's see, it's probably Rob. Let's go ahead and boot him from the server. No, he's good. Okay, cool. So that's combustion reactions, okay? Right now, again, we're just focusing on figuring out what the products are. Okay? That's okay. Don't worry, Rob. We only have like 4 more meetings, so we don't care anymore. By the way, look who we have today in a happy line. We have a creature, we have Oz, and then we have Kaz. All of them just sleeping in a little row here. So we'll see if the creature wakes up. We'll hear what he has to say about this stuff. Nice. I'm glad you got paid. Okay. So, the next thing that we're going to do with these chemical reactions is we're going to introduce states of matter. Okay, so those are going to be important for when we want to predict what's going to happen. For example, if we were to take this reaction, first off, what type of reaction is this going to be? We have synthesis, decomposition, single replacement, double replacement, or combustion. It's double displacement, right? We have 2 compounds coming together. So what are the products going to be? So this is what you've done on your lab, right? Let's see who's going to get it. Yes, very good. So remember, you just kind of switch them apart. You know that this is potassium plus with SO42 minus. You've got calcium 2 plus and chloride minus. You're just going to kind of swap those. Great. So thinking back to what we learned in the last chapter, if we were to think about the solubility of these compounds, if I tell you that these 2 were aqueous, what would you expect the products to be? So that would be the calcium sulfate and the potassium chloride. Are you sure about that? I'll tell you, yes, this one will be aqueous. Okay, think back to, we learned some solubility rules last chapter. So let's take those now into our brains. We may remember that sulfates are typically soluble unless they have calcium, right? So calcium is going to be, the calcium sulfate is going to be solid. Oddly enough, Samvel, although I make sense, we typically write solid, liquid, gas, or aqueous. So in the case that it's insoluble, the letter will be S for solid. Okay? And so what this means is that as this reaction happens, you're going to have solid forming in your reaction. And so you'll have seen these on your lab last week. This is called precipitation. And that might not be immediately like big chunks of solid. Sometimes just the solution will turn cloudy. And that's enough to indicate that there is something solid or insoluble forming within your reaction. So if you look back to some of the ones you did for your experiment last week, you'll see some of them are kind of cloudy after they've been mixed together. That's precipitation. A solid has formed there. Okay? So we will want to incorporate what we learned last chapter with which compounds will be soluble and which ones will not. Remember, since this is open book, you can totally have your little cheat sheet of what's going to be soluble and what's not on your exam. So you will be kind of expected to be able to predict if you're going to form a solid. Open universe indeed. So you'll want to kind of practice with that. I'll give you another example. How about we do, let's see. Okay. Again, we're going to just take into account that our reactants will be aqueous. Reactants could be solid, could be aqueous. It's whatever is given to you, so you don't ever have to worry about that. It's the products, though, that you're going to want to worry about what's soluble, what's not. So what are the products we get here? Alright, let's see. We got Marissa and Samville. Oh, you guys are so good. Wonderful job. Absolutely. So, sodium bromide, our first one, definitely going to be soluble, right? Anything with sodium is soluble. Bromides are also soluble unless they have silver, mercury, or lead, so we're good there. And both of them have indicated that we're going to get water, which will be a liquid, plus carbon dioxide, which will be a gas. So remember, technically you're going to form carbonic acid as the second product of this, but we remember that carbonic acid will always turn into water and carbon dioxide. Just so you know, that water will always be liquid, and those three, the carbon dioxide, sulfur dioxide, and ammonia, are all gases. Okay, so those are the 3 times you're going to see gases in double displacement reactions. Let me just write this down at the bottom. The only time you're going to see gases is going to be CO2, SO2, ammonia, or hydrogen sulfide. Okay, those will be the gases that you'll see in reactions. So anytime these are products, those are going to be gases. Okay? And so in this case, since we had carbon dioxide, that is going to be a gas. Okay? And typically you'll see this as bubbles. Technically, you'll see the first 2 more as bubbles. The ammonia, you don't really see bubbles because it's very soluble in water. So you can just kind of detect it with your nose. The same with the hydrogen sulfide. Stinky. That's your rotten egg smell. Yeah, not nice. Okay, cool. So let's talk about things that will be liquids then. So thankfully, there's just a few things that are going to be liquids. You're going to have bromine is a liquid at a room temperature, normal conditions, and water will be a liquid. But also notice when not combustion. Because in combustion, the water will actually be a gas. All right, and I mean, you've seen a campfire, you've seen a stove, you don't have just water droplets in the middle of whatever you're doing, right? It's always going to be a gas coming out because it's just so hot, right? Fire is hot. combustion reactions are a very high temperature, so you're going to boil up any water that you produce. Okay, however, in all other reactions, your water will be liquid. Okay? Let's see what Samvel's got to say. And bromine is the only other one that will be liquid. Okay, and that's just Br2. Okay, while he's typing, back to our old friend, the periodic table. Just remember, I mean, you'll be able to look these up, but we had the noble gases are going to be gases, of course, at room temperature, but those aren't going to be in reactions anyway. Fluorine, chlorine, oxygen, and nitrogen, these guys are all gases as well. So is hydrogen. Bromine's a liquid, and pretty much everything else on this periodic table will be a solid. That's correct, Samvel. Both the CO2 and the water will be gas for combustion reactions. Okay? Exciting! Okay, so let's do a couple more. Let's go back to this one from before. So remember the reactants, I'm not going to ask you for their states of matter because that will always be given to you. So there will be some, because these reactions are taking place in a certain medium, that'll be given to you. So, what type of reaction is this, first of all? Single replacement, right. So, we are going to kick out the bromine, right? Because chlorine is a nonmetal. We're going to look at our compound. We're going to kick out the nonmetal. So we're going to make KCl plus Br2. Remember that bromine is one of those Hofbrinkel elements that always comes as a pair. All right, KCl we've already said is aqueous before. And bromine, what do we expect its state of matter to be? Liquid, yes. So bromine will be liquid. Okay? So this is just a matter of practicing, so there will be plenty of homework for you to do that. Yes, yes. And I'm sure you've been working on your experiment 4 as well, which has got plenty of reactions for you to play with. Cool. Okay, so now, in that case, let's get on to this pesky task of balancing these equations. So for a while, you've probably noticed, hey, we have Br2 on one side of this reaction, but we just have Br on the other side. And we remember way, way, way back when, maybe when we were in person, we talked about matter not being able to be created or destroyed, right? So this bromine has to have come from somewhere, right? We can't just have a bromine popping out of nowhere. And so we're going to actually balance this equation by making sure that everything on the reactant and the product side are equal. So we're going to want to go ahead and kind of just make a table of all the components of our reaction. And if we look, we can kind of establish how many of each one we have on each side of the reaction. So if we look at potassium, if we look on the left, the reactant side of the equation, we just have one potassium, right? KBr has one potassium in it. On the product side, potassium has also one, just because we have one potassium as part of that KCl, sorry. If we look at bromine next, we have one bromine on the left. Aha, but now we have two bromines on the right, and we have two chlorines on the left, and one chlorine on the right. So this reaction is not balanced. Okay, it does not have the same amount of atoms on one side as the other. So how do you think we're going to go ahead and fix this problem? Perhaps you've already learned, but the only thing we're allowed to do, we can't change these compounds, okay? So what we're going to have to do is just make more of the same compounds. So, yeah, we're going to multiply them. So if we think, what's the potassiums are already okay so far. So we're going to look at these bromines. We have one bromine on the left and two on the right. So what we're going to do is make it so that the left side has two bromines. And how we're going to do that is by putting the coefficient of 2 in front of our KBr. Once we do that, just switching to another color, notice we will now have two potassiums on the left and two bromines on the left. So far, so good, I hope. We can keep going down. We can see chlorine has 2 on the left, 1 on the right. So we're going to do the same thing, right? We're going to add an extra potassium chloride. And so now we want to correct our numbers to indicate what the new quantities are. And now we just want to make sure that all of these are equal. So the left we have 2 potassiums, the right we have 2 potassiums. Left side we have 2 bromines, right side we have 2 bromines. Left side 2 chlorines, right side 2 chlorines. Okay, so it's just kind of a matter of somewhat guess and check, but it's kind of like thinking about it a bit more logically. Okay, so this is what's called balancing a reaction. All right. This reaction is now balanced. Hooray! So balancing is the process of coming up with these coefficients. Okay? So let's now go ahead and look at a couple more. We've already done this reaction. So let's do this one. I want you guys to complete the reaction, figure out the states of matter, and balance it for me. We're going to do all 3 things here. I'll just go ahead and indicate right now these guys are aqueous. Though, actually, since we are fairly limited on time, I'm just going to go ahead and I'll predict the products for us. So we're going to get calcium phosphate, which will be solid, and sodium chloride, which will be aqueous. Okay, remember, phosphates are not going to be soluble. Well, I mean, the calcium phosphate is not even on our list, so that's why it's going to be insoluble. Okay? So, looking at this, if we have... one thing I want to let you guys know is when we're balancing, we can have our reactant and product side. If we're looking at calcium, chlorine, sodium, whenever you have a polyatomic ion, it's just smarter to keep it together, because the polyatomic ions are going to stay as polyatomic ions. They're not going to kind of explode or anything. So it's a lot easier if you just keep the polyatomic ions together. You could count the phosphorus and oxygen separately, but that's going to make things more confusing, and I don't suggest you do it. So I would keep polyatomic ions together. Keep polyatomic ions whole. Okay, so looking at this, we see we have 1 calcium on the left, and we have 3 now on the right. We see that that subscript 3 underneath the calcium indicates there are 3 calciums as part of that compound. We have 2 chlorines on the left, 1 chlorine on the right, 3 sodiums on the left, 1 on the right, 1 phosphate, 2 phosphates. Alright, so hopefully none of this is super confusing, just counting how many of each we currently have. Alrighty, so now we're going to go ahead and look at these numbers and see how we're going to fix them. So we have 1 calcium versus 3 calcium, so solution here is we're going to multiply that calcium chloride by 3. That'll increase our number of calciums. However, it also increases the number of chlorines. So remember, every time you're messing with these coefficients, you have to adjust your table here. All right, and so we now have 6 chlorines on the left, 1 on the right. So we're going to have to make that one have 6 now. And if we look here, that's going to make our sodium 6. If we look at the sodium on the left, we have 3. So if we want to make that into 6, we have to multiply it by 2, right? Because 2 times 3 is 6. So that'll give us 6 there. And it'll also give us 2 phosphates. And if we look, now everything is happily balanced, and we will have finished our reaction. All right, so we have balanced it now with these coefficients, 3, 2, 1, and 6. Anybody have any questions on this? You're going to want to do this for all your stuff for your thing tomorrow, the lab that's due tomorrow, by the way. Okay, so balancing is where we're finding these coefficients. All right, let's see what Marissa's got to say. Ah, awesome. Okay, well, I'm glad to hear that. So, yeah, you always just want to count up your atoms or polyatomic ions and make sure that you have the same number on both sides. All right, cool. So, let's see, how about another one? Let's do that pesky propane combustion. So remember, you're always going to get carbon dioxide and water, right? This one's going to be a little bit more tricky. Propane's a gas typically, so we'll just make all of these gases. This one is going to be a bit more complicated because we have multiple things with oxygen on the right side of the equation. So this can get a little tricky, so let's go ahead and just work through it together. Reactants, products. Putting the R on the left side just makes me crazy, by the way, because I'm so like right and left, which one's which? Okay, so let's go ahead and count. We have 3 carbons on the left. We have 1 carbon on the right. We have 8 hydrogens and 2 hydrogens. And we have 2 oxygens and 3 oxygens. Alrighty, so again, I typically just go from top to bottom. With combustion in particular, again, it does not matter which one you balance first, but you do want to kind of save oxygen for last, because that's going to be our most complicated one. Okay, so let's see here. If we have 3 on the left, 1 on the right, we are going to multiply this by 3. Yes? So now we have 3 carbons. And now let's double check our oxygens. From carbon dioxide, we currently have 6 oxygens, right? However, we do have 1 more coming from water, so we can't forget about that one. So in fact, now we have 7 oxygens. 6 from carbon dioxide, 1 from water. Alrighty, if we look down to hydrogen, we see now that we have 8 versus 2. So we're going to want to multiply this one by 4. If we do that, this is going to become 8. And now we're going to have to count our oxygens again. We have 6 from carbon dioxide, and we have 4 from oxygen, or from water. Putting that together, that is 10. Okay? And so now we look at our oxygen on the left. We have 2 versus 10. So if we want to make that work out, we're going to have to put a 5 there. And that'll make it have 10 oxygens. Okay, so the only thing that's a little bit harder here is that we now have to just keep track of oxygens with 2 different compounds. Okay, so that's the only thing. Is every time you're changing one of the ones on the right, by changing its coefficient, you have to remember that oxygen is going to change as well. Okay, is that one okay? Alrighty, so let's up the ante one more time. Okay, I'm going to show you the most difficult type we're going to have to deal with in this class. Alright, and this will be a very similar problem. Same thing as before. Again, we're going to go ahead and assume they're all gases. Totally a good assumption. We have the reactant side and product side. We have carbon, hydrogen, and oxygen. If we are going to start, we have 4 carbons on the left, 1 on the right, 10 hydrogens, 2 hydrogens, 2 oxygens, and 3 oxygens. Alrighty, here we go. So just like before, we are going to go ahead and fix our carbons first, just because it's the top one. So that means we have 4 carbons, and now we have 4 times 2, that's 8, plus 1 is 9 oxygens. Okay, so let's go to hydrogen now. We see that we're going to want to make this 2 into 10 by multiplying by 5. Okay, let's go ahead and check our oxygens. We have 8 from carbon dioxide and 5 from water. That becomes 13. Oh dear, we have a problem now. How are we going to make 2 and 13 work out together? That's going to be kind of a pain, right? So this goes back to that kind of, if you remember with charge balancing, it's that greatest common, or least common multiple, I guess that's what it is. So if you ever have ones that are not compatible, we can't make 2 into 13 very easily. Let's just multiply them by each other. Okay, so we're going to make both of them into 26. So if we want to do that, if we make this one 26, we're going to have how many oxygens up there? I mean, it'll be 13, right? In order to get 26 oxygens. And if we want to make this one into 26, that means since both of the compounds on the right side are going to be doubled, all we have to do is double their coefficients. So it was 13 before with our 4 and 5 there. If we want it to be 26, we'll just double them. All right, and as a result, we're going to have to do some adjustment. And now we see, okay, we have 4 carbons on the left and 8 on the right. So we're going to need to go ahead and put a 2 in front of that butane molecule there. And there we go, we've lost the screen. Let's go ahead and fix that. Okay, cool. So with that in mind, we can go ahead and adjust these, and we should see now that everything is going to work out. Yeah, I know, right? This is like the 3rd cable I've used for you guys. Go figure. It's just Microsoft Connect is crap. That is our answer to this problem. So, yeah, go figure. Okay? Is that one okay? Alrighty. Let's see, Marissa's got something to say. Yeah, of course. Okay, try and solve this one on your own. I'll go ahead and put the gases there. No, goodness. Okay, let's see. This thing should be able to do it wirelessly. Let's see if that'll be better. Okay, we've disconnected the cable. Let's see if this will be nicer. Some days the Wi-Fi works better, some days it works worse. It seems to be better. Okay, go ahead and work on it. I'll do it in my head if I can. Let's see. All right, let's see. Rob may have it. Let's see. Oh, no. You're good. You're good. Yeah. The utter silence. I love it. Yes. It's because Creature has not started working yet. Almost, Josh. Pretty close, but not quite. Because if you look at your oxygens, you're going to have 15 on the right from what you've written, and you'll have 20 on the left. So that's not going to be quite what you're looking for. You're getting there, though. Yeah, that's what I got as well, Sample. Very nice job. So yes, you should get, well, let's see, let's just go ahead. You start with 5, 1, 10, 2, 2, and 3. So you go ahead, you're going to start putting this one up to 5, and that'll be 11. If you do the hydrogens next, you're going to get 15. One thing you can do here, you can say technically this is just 15 over 2. That would totally work, but because we like to have integers instead of fractions as our coefficients, what you're going to want to do again is double everything. So if we double everything, we're going to see that this one becomes 2, this one becomes 15, this one becomes 10, this one becomes 10, and so that'll work to get you the right answer. Okay? Let me make that 15 a bit neater. Okay? So Sample is right. That is what you should get for balancing this equation. I'll give you guys some, I'll find online some practice for you guys to do just so you can be able to see your answers and check that you're doing these correctly. Because I know that this particular one does take time to master. Okay? but we're on a schedule, we must keep pressing forward. Okay, so I will give you more practice on balancing equations so that you can practice those at home. Not that you're doing anything different here, but we're always at home, right? So, okay. So, with that in mind, I want to move to our next topic. This is one that is covered on your lab due tomorrow, so I want to talk about that. And this is a way of simplifying equations just so we can see exactly what chemistry is happening here. So, if, for example, we take that, we had this one, right? And we saw that that's going to produce this guy when we do all the balancing and everything. Alrighty, so we're going to want to see exactly what's happening here chemically. There are going to be things in this solution, because this reaction is taking place in solution, that actually aren't doing anything. So if we remember that ions that are aqueous are kind of just floating around with water surrounding them. They're not participating in any chemistry per se. So what we're going to do is we are going to go ahead and find what is called a complete ionic equation. And what we are going to do is we are going to break all aqueous things into their ions. Alrighty, so what is CaCl2 made of? We'll do this one in blue. If we were to put that into solution, what would happen to that? What would we get out of that? It's similar to that Van Hoff thing that we talked about before. What are we going to get when we dissolve CaCl2? See, we've had Zoe typing, and then she vanished. Let's see what Samvel's got to say. Aha, almost. Almost, Samvel. So, we are going to have calcium, but we're actually going to put the 2 out over there as a coefficient. So it's not going to necessarily... No, you're good. Yeah, you're good, Zoe. So, because remember, Cl2, that's elemental chlorine. That's not the same thing as ion chlorine. Okay, so this one on the left, that's what we would have if it was just by itself. But since it's an ion, there's going to be chloride minuses. Those do not come together with the subscript 2. Okay? Cool. Okay, so let's do erasing that. We are going to designate that all these are aqueous. Okay, if we break apart sodium sulfate, what are we going to get? In this same idea, we're going to get 2 sodiums, right? Because there's 2 sodiums, part of that sodium sulfate, plus 1 sulfate ion. All right, since I don't have much room, I'm just going to do the... well, let's see what we can do. I'll try, okay? Calcium sulfate is solid, so we do not mess with it. Remember, when we're doing this, we're breaking apart aqueous things only. Okay, so leave solids, liquids, gases alone. And if we look, we have 2 sodiums plus 2 chlorines. All right, that 2 sodium chloride tells us there's 2 sodiums, 2 chlorines. Okay? So, if we look at this, we're going to notice that, you know, for example, if we had a math equation, I don't know, 2 plus x equals 5 plus 2. Remember, in math, if we have the same thing on both sides of the equation, we can just get rid of it, right? And we can see that if doing this, x is equal to 5, right? Just algebra. We can do the same thing with our chemical equation. We can see what's exactly the same on the left side, on the reactant side, versus the product side. So on the left side, we have Ca2 plus aqueous. Do we have that on the right side? Exactly written as Ca2 plus aqueous? No, we don't. So we're going to leave it alone. How about 2 Cl minuses? Do we have 2 Cl minus aqueous on the other side of the reaction? Yeah. So those we can get rid of because they're unchanged throughout the reaction. So on the left side of the reaction, we have chlorides surrounded by water, right, because they're dissolved. On the right side, we have chlorides surrounded by water. Nothing has happened to the chlorides. Who cares about them? All right, how about the sodiums? Do we have sodiums on both sides that are identical to each other? We do. We can get rid of them. And we see we have sulfate on one side. We do not have sulfate on the other side. So we have special names for these. We call them spectator ions. And that's going to be our sodium and our chloride. Those are present. Oh my gosh. Yes, computer, you can do it. There, I plug it back in. There we go. Okay. Those are, what was I going to write? They present on both sides. Okay, so hopefully now that should be fixed, Zoe, since it had killed itself for a second. That unfortunately is Microsoft, so that has nothing to do with Discord or anything like that, so unfortunately. So we're going to have what's called a net ionic equation. And this has spectator ions removed. I know, right? So, if we remove the spectator ions, we're going to have calcium 2 plus, basically everything that's left over after we canceled the others out. And that's turning into CaSO4 solid. Alright, so this right here is the net ionic equation. So this tells us exactly what's happening there. And so it doesn't matter if instead of chloride we use bromide as the anion, or if we use potassium as the other cation, does not matter. Those will just be spectators. They're not going to actually do anything with the chemistry. What's actually happening here is calcium ions and the sulfate ions are coming together to form solid calcium sulfate. Alright, so this is the net ionic equation. We've identified which ions are present on both sides. Those are spectators. And we have removed them from our equation. And then we have just copied what's left over. Okay? Let's do one more of those before our break. Let's go back to when I did in the textbook for you guys. Go ahead. Balance it for me. Predict it. Actually, first of all, what type of reaction? Come on, type of reaction shouldn't take that long. Yeah, single, right? Element plus compound, right? So, copper, metal or non-metal? Metal, right? So it's going to kick out the silver, right? So, if it's going to do that, we're going to have silver by itself. And remember, we're going to assume that we get copper 2+, which tells us this will be the compound that we're going to form. Remember, we assume Cu2+. Alrighty. What do we expect the solubilities of these to be? Consider if you've ever seen silver metal, does it dissolve in water? No, of course not. I mean, that'd be really sucky. You know, you're wearing your earrings in the shower and all of a sudden they melt away. Forget it. No. Metals are going to be solid, remember? I mean, just like you have copper cookware or anything, you know, it would really suck if those dissolved in water. Not going to happen. Okay, however, we'll remember that all nitrates will be soluble. So the silver nitrate and copper 2 nitrate rather, should both be soluble. Okay, so let's go ahead and do our complete ionic. This one, by the way, is called a molecular equation. If we do complete ionic, oh, by the way, we have to balance this. Can someone balance this equation for me? You know, we don't have time. I'll just do it for us. Ta-da! Okay, now it's balanced. Okay, complete ionic. Let's go ahead and break apart our aqueous things. So, copper solid, leave it alone. Does not change. Only aqueous stuff we break apart. So, we're going to have 2 silvers and 2 nitrates. Both of those will be aqueous. And we're going to have 2 silver solid plus Cu2 plus. Oh dear. Sorry again. Poor planning. Oh gosh, and my face is in the way. How embarrassing. Okay. There we go. Alrighty, what's the same on both sides? Is it? Is Ag plus Aq the same as Ags? They have to be exactly identical. Yeah, the only thing that's identical on this one is the nitrates. The nitrates are identical, but remember, 2Ag plus Aq is not the same thing as 2Ag solid. Okay, they have to be exactly the same. Charge, number of them, state of matter, everything has to be the same. So with those nitrates, we have exactly 2 nitrates. They're both aqueous on both sides of the equation. Okay, so if we go ahead and rewrite our equation as the net ionic, I'll be able to give you practice with this one as well. We're going to have copper plus 2 silver ions turns into 2 silver solid plus the copper 2 plus ion. For which one? The silver? Okay, so remember with single displacement reactions we have element plus compound turns into element plus compound. So if you look, the copper didn't have a charge on the left side of the reaction, just normal metallic copper. When we kick out the other ion, we're going to be forming the elemental form of the other metal. And so silver in its normal state is just a solid. It's just a metal, right? It's not necessarily an ion, because if it were an ion, it would have to be part of an ionic compound. Okay, so with single replacements, you're always going to have a neutral element kicking out a charged element and replacing it. Okay, so in this case, copper metal kicked out silver ions to make silver metal plus copper ions. Okay, and before we had chlorine gas, elemental chlorine, kicking out bromide ions to make bromine liquid plus chloride ions. So same thing. So you're going to be making one of them into an ion, and you're going to be taking the ion that used to be there and making it into neutral. Ooh, what a day. Okay, we've had quite a bit. Let's go ahead and take our break. Definitely have earned it. We've done a lot. We're going to do another one of these when we get back. And then we're going to talk about some redox chemistry, and it'll be fun. Okay, cool. Go ahead, take your break. Let's see, how about 4:37? Yes, Josh, that's correct.